Hi, my name is Mike Splash. I'm Senior Hydrogeologist at the Dragon Corporation. Dragon is an environmental consulting firm with offices in the United States and Canada. I'm hosting this series of webinars that provides you with 10 tools that will help to solve your groundwater contamination problems. And today I'm working with Fatima Vakili, one of my associates, and we're going to talk about environmental isotopes in today's webinar. So these are specialized tools that allow us to evaluate groundwater flow and fate and transport independent of the typical tools that you would use, such as Darcy's law and transport models and so on. So we're going to introduce you to isotope hydrogeology and talk about some case studies. So isotopes are simply atoms with the same number of protons but different number of neutrons in the nucleus. So that means that the nucleus of the atoms will have different mass. Therefore, they behave differently in the environment. An example is an apple. An apple is kind of generic for different varieties of apples like Golden Delicious or Rhode Island Greening and so on. They're basically similar, but they have slightly different characteristics. I also use the example of cars. In the heyday of the Motor City, you had like 5 different types of GMs and 5 different types of Chrysler cars that were basically the same but just had different badges. So isotopes are atoms that have different characteristics or behaviors because of their mass differences. So we're going to talk about isotopes in water, and we're going to talk about isotopes in target chemicals like contaminants. So first of all, I'm going to talk about the environmental isotopes in water molecules. We're going to focus on hydrogen and oxygen isotopes. They make up the water molecule. These are naturally occurring isotopes that we find useful for solving hydrogeologic problems. We can use them in natural tracer tests on a very large scale to determine the age of water. And we've got some different examples that we can look at. And, the one that I just put up on the screen shows a pond on the left and wells on the right in the yellow. And the question is, does the ponded water affect the chemistry at the monitoring well? And we can answer this question by looking at oxygen and hydrogen isotopes. And another test that we can do is if we're looking at runoff in a catchment, when did the water in the stream originate? Is it water from the current precipitation event, or is it water from previous precipitation events? We can determine that with isotopes. So the isotopes that we're looking at are, as I said, hydrogen and oxygen isotopes. Hydrogen has 3 isotopes, H1 called protium, H2 called deuterium, and H3 called tritium. Oxygen, we mainly deal with 2 isotopes, oxygen 16, which is the common isotope, and oxygen 18, which is the heavy isotope. So on the right column, you see whether it's stable or radiogenic, and all of them except tritium are stable. Tritium spontaneously decays, and we'll talk about that in a few minutes. So some of the uses that we can have for these isotopes are, so the protium and deuterium, we can look at mixing of water bodies, evaporation of water bodies, long-range age dating, and I'm going to talk about that in a case study. Tritium H3 we can use to identify mixing between groundwater bodies, and short-range age dating of water bodies. And finally, oxygen 16, oxygen 18 are like the protium deuterium. We can use it for mixing, evaporation, and long-range age dating. So the kind of the basis of how we can use the water isotopes is that lighter isotopes tend to be more energetic and want to be in the vapor phase. So we get the heavier isotopes preferentially looking for being in the liquid phase, and the lighter isotopes tend to evaporate more readily and go into the atmosphere and participate in the hydrologic cycle. So what does all this mean? This is a map from the International Atomic Energy Agency website, IAEA, and it shows the aerial distribution around the globe of oxygen 18 concentrations. We can see these down here by color coding in precipitation. So this is based on many years of records. The dots show the recording stations. So one thing we see from this is isotope concentration, the oxygen 18, and precipitation depends on location. So for example, where we are up here in the Great Lakes, you can see kind of yellowish color. It's minus 10 is the mean annual oxygen 18 concentration in that range. But if you were to go into the Arctic, you would see that you're down here at minus 27, minus 22, or the Antarctic. And if you go to equatorial areas, you see close to zero. And that all is a function of the temperature and the energy that the light and the heavy isotopes have. So geographically, there are differences. Groundwater takes on the mean annual precipitation value. So, you know, the runoff process will change things a little bit, but in general, if you looked at the precipitation map, you could get a pretty good idea of what the groundwater oxygen 18 concentration is like. So again, looking in our area of the Great Lakes, we're about minus 10. That's what we'd expect to see. But individual precipitation events can be isotopically distinct from the groundwater. And that allows us to compare like rain runoff, for example, to the groundwater, and we might be able to differentiate those two. And also what we find, and we'll talk about this a little bit later on, that we can use oxygen 18 or deuterium in the groundwater as an indicator of long-term climate changes and age indicators. For example, right now we see again in the Great Lakes area, minus 10 in the groundwater. That's what we'd expect. But as I'll show you later on in the case study, we have values that looked like they were in the Arctic in some groundwaters, or in the Antarctic. And that's because we've had different temperatures occurring at our location over time. So we can use this as an indicator of old groundwater. If it's present, we'll be able to detect that. So we can look at groundwater contributions storm runoff. This is where I started doing my research a long time ago. And it's still used to evaluate groundwater contributions storm runoff. This is important in things like legacy nitrate that is not the result of current agricultural use, but old agricultural use. We can determine the age of the water in the streams, acidification, and deforestation issues. Those are some of the things we use in surface water. And in groundwater, we can determine whether an aquifer is protected by surface sources of contamination. We can determine if groundwater is fossil, meaning thousands of years old, and I'm going to talk about that in the case study at the end of this webinar. So another isotope that we use in the water isotope group is tritium H3. It's a naturally occurring isotope. It's also man-made or anthropogenic. Concentrations are in tritium units, which are 1 tritium isotope in 10 to the 18th hydrogen isotope. So it's very precise, has to be analyzed in specialized laboratories. Natural tritium isotopic concentration is somewhat under debate, but less than 25 tritium units is generally considered to be the value of natural tritium in precipitation. But what we see is this trend in the graph is that it's changed. Tritium concentrations have changed with time. This is a log scale. Each major unit is a factor of 10 concentrations in tritium units, 1950, 2020. The data are for Ottawa. There are other stations where this has been measured, but tritium has the longest record. So atmospheric testing of nuclear weapons in the 1950s created tritium, and tritium increased in concentration in precipitation from about 25 in some places, thousands of tritium units in the groundwater. Then in 1963, in here, the USSR and the United States signed the Atmospheric Test Ban Treaty, and as a result, there was limited input of anthropogenic tritium after that. And the other factor that we have in tritium is that it's radiogenic. It breaks down with a half-life, and I've got the symbol in there, half-life that we use of about 12.3 or 12.4 years. And what that means is that if you start off with a pound of tritium today in 12.3 years, you'll have half a pound, and another 12.3 years, you'll have a quarter pound. So tritium spontaneously decays. So we can use that information to help us determine the age of a fairly recent groundwater. This is a couple ways we use tritium. So we can tell if tritium is pre-1950. So if there was natural tritium in the groundwater and it was protected from more recent precipitation, you would now have virtually non-detect tritium. If you had your groundwater recharged in 1963, this is the projection of what that decay would be. You would see that about now you should have somewhere around 100 or 200 tritium units if that water moved through the aquifer system by itself. And the same thing for 1970. So you can get an idea of fairly recent groundwater ages based on tritium. So now I'm going to turn it over to Fatima, and she's going to talk about compound-specific isotope analysis. And I'll be back when she's finished.
Hi, my name is Fatima Vakili. I did my master's and PhD in contaminant hydrogeology at the University of Waterloo. My PhD research was focused on the effect of physical processes on isotopic signatures of chlorinated solvents. I joined Reagan just over a year ago. Today I will talk about compound-specific isotope analysis, or CSIA, as an advanced tool to solve groundwater issues. So what is CSIA? It means that if you have a groundwater sample with a mixture of compounds like TCE and CCCE, first those compounds are separated using gas chromatography, and then the isotopic ratios of each compound are measured individually using mass spectrometry. This table shows stable isotopes for common groundwater contaminants such as petroleum hydrocarbons and chlorinated solvents and nitrate. This plot shows carbon versus chlorine isotopic ratios of chlorinated solvents from different manufacturers. So for example, blue diamonds are TCE from Dow, ICI, and PPG. So as you can see here, they have distinct isotopic signatures. So let's assume there are two dry cleaning operations. One of them used TCE from Dow, and the other one used TCE from PPG, and a TCE release happens. So we can use isotopes to find out who is responsible for the release. This is a case study that was done by Honkler and others. This is a site in Kitchener, Ontario. Groundwater moves from south to north. And this is the TCE plume. So they collected groundwater samples along the plume and analyzed them for concentrations and carbon isotopes. As you can see, concentration decreases with distance from the source, but isotopic signatures remain the same. Therefore, dilution is the main process in this site, and no reactive processes such as biodegradation are happening. I will explain in the next slide how biodegradation affects isotopic signatures. So if we have a TCE solution with a mixture of molecules with heavy and light isotopes and add bacteria to the solution, bacteria prefer to break down the TCE with light isotopes. Therefore, the solution gets enriched in TCE with heavy isotopes over time. This is a dual carbon and chlorine isotope plot that shows the isotope trends during aerobic oxidation and reductive dechlorination of vinyl chloride and cis-TCE. This plot is from Abe et al. Paper. As you can see, isotopic ratios shift toward positive values over time. So the important point is that the slopes are also different for aerobic oxidation and reductive dechlorination. So we can use dual isotope plots to distinguish between different processes. This plot shows the isotope trends for TCA or trichloroethane during different reactive processes using persulfate, zero-valent iron, and hydrolysis and dehydrohalogenation, which is a substitution reaction. As you can see here, again, each process has a distinct isotope trend. So, for example, if we use persulfate and ZVI in the field for remediation, we can use isotopes to evaluate the progress of each method. This is a dual carbon and hydrogen isotope plot from Butchart et al. Paper that was published in 2018. This plot shows expected isotope trend for benzene during different processes such as biodegradation, chemical oxidation, and physical removal processes. For example, if our isotopic ratios fall in this area, in the light green area, aerobic biodegradation is the dominant process, and if they fall in the purple area, chemical oxidation is the dominant process. Now I'm gonna talk about a case study where there were two TCE hotspots, one in the up gradient and one in the down gradient, and we used carbon and chlorine isotopes to investigate whether the down gradient TCE was originated from the up gradient TCE. So as I mentioned, we had the up gradient hotspot, which we call it TCE-A, and down gradient hotspot, which we call it TCE-B. This is the groundwater flow from TCA to TCEB. And there was an evidence of biodegradation in the groundwater in this site. So if we assume TCEB is originated from TCEA, and we take some groundwater samples from up gradient and down gradient. So the travel time for up gradient samples is shorter than the travel time for the down gradient samples. So it means that the down gradient samples must be more degraded than the up gradient samples. And if you analyze up gradient and down gradient samples for stable isotopes, we would expect that the down gradient samples are more positive than the up gradient samples because they are more degraded. But what we observed was different. So the up gradient samples were more positive than the down gradient samples, which means that TCEA and TCEB are two different releases. So how we can use hydrogen isotopes to identify different sources. So here you can see the reported hydrogen isotopic ratios for TCE as a byproduct of PCE degradation, and isotopic ratios of manufactured TCE. So as you can see here, manufactured TCE has highly positive values, but TCE from PCE biodegradation has negative values. So if we have a TCE plume, which is like byproduct of PCE, and which we call it plume A here, and we have another TCE plume nearby, which we call it plume B. We can use hydrogen isotopes to see if these two plumes are originated from the same source. So if we take samples 1, 2, and 3 and analyze them for hydrogen isotopes, if the hydrogen isotopic ratios are the same, it means that these two are from the same source. But if sample 1 falls in this area, sample 2, which is from the mixed zone, falls in this area, and sample 3 falls in this area, we can say that they are from different sources. So as a summary, CSIA can be used as a robust tool to identify different sources of contaminants in the subsurface, identify contaminants, mass removal processes, and also it can be used as a diagnostic tool to improve the efficiency of remediation system. Now Mike will finish it up with a case study using oxygen isotopes.
So I'm going to do a case study that's actually one of the earlier groundwater case studies that I worked on, and this was done a number of years ago with graduate students pre-Dragon. So what we see here is this is the lower Great Lakes area. This is Michigan and Ontario, Lake Erie, Lake Huron, Lake St. Clair, Detroit River, St. Clair River. And generally what you have in this area, it's glaciated. There's a thick clayey overburden, 100 feet or 30 meters, overlying a freshwater aquifer that's at the surface of the bedrock. And groundwater generally flows towards the lakes and connecting channels, as we see in the arrows. So what we want to know in this area is the freshwater aquifer protected from surface sources of contamination. And this arose when there was some discussion about using the clay soils for nuclear waste repositories, and also it also comes up when you're looking at conventional landfills and whether there will be an effect on the underlying aquifers. So we go back to this map we saw before from the International Atomic Energy Agency, showing the global distribution of precipitation, mean annual precipitation. So we're up here again in the yellow. About -10 is our typical groundwater that is shallow. This is a map from one of my graduate students who looked at groundwater. His Bessie Chernikrak thesis. And what we see here is color-coded with about -10, the concentration, recent precipitation in the darker colors, and the lighter colors are -14 to -18. So how can you explain this if the concentration that we're seeing in precipitation is -10? These -14 to -18s are characteristic of Arctic or Antarctic types of precipitation. So how do we explain it? Well, part of the explanation, we can look at work that Tom Edwards did at the University of Waterloo. And what he did was he looked at oxygen 18 in freshwater shells and ancient trees, and basically found this type of distribution. So time on the y-axis, oxygen 18 on the x-axis. And what we see is fairly recent, the last few thousand years, we're in that kind of the -10 range. But when we go 8,000 to 12,000 years ago, the average precipitation in this area was, it was glacial. It was much different from what we have now. So I had some graduate students also look at the overlying soils and what the groundwater in the clay above the aquifer showed. So this is compiling that data. So Tom Edwards data, so age with oxygen 18 are these green dots, E for Edwards, and two graduate students, Osman Ibrahim in the red dashed line, I for Ibrahim, and Andrew Ainslie, A for Ainslie, A for Andrew, over here. So Osman Ibrahim's data were here. So this is showing the freshwater aquifer. It was glacial, -18, -16. And Andrew Ainslie's were here, so showing more recent. So what can we get from this data? Well, one is that the aquifer, when we get close to the surface water bodies that discharge, is protected. So you could put in landfills in these lighter colored areas because the groundwater there at depth is very old, meaning doesn't move very quickly, meaning you're not going to impact the aquifer. Whereas if you look in some of these areas here with the darker blue, groundwater could be recent, landfills in that area could be problematic. So that was a regional investigation that looked at both the Aquitard overlying the aquifer and the aquifer, which gave you ages of groundwater that span thousands and thousands of years. So another question or another case study for another time is to explain to you why this area of groundwater here is younger, and it's actually pretty fascinating related to glaciation of the area. But that's about all the time we have today. Just in summary, we've talked about environmental isotopes that help us to understand groundwater flow and chemical transport and fate. And the reason why it's a good tool to use is that it's an independent tool. We don't have to rely on Darcy's law. If you have fractured rock, that becomes very complicated. The isotopes will still work the way they're going to work. So it's very useful for unraveling complex problems. So thank you for watching today. Our next installment will be looking at specialized tools modeling and how you can use that with the other 7 things we've talked about previously to help you to understand your groundwater flow and contamination issues. So again, thank you. If you want to be informed about subsequent webinars, you can sign up for our newsletters at dragon.com or dragon.ca, or contact Alan Hahn if you want to learn more about Dragon, including our peer services. There's the link that you can look at. And if you want to contact either Fata or myself, you can get us at our email address or our phone number, 248-932-0228. Thanks a lot. Hope to see you later.